Okay. Yeah, so before getting to those 3 results from our group, of course, just this is a group effort. So I have a photograph of our group here at University of Colorado. Some faces here should be recognizable. Jamie and Dennis, if you're able to follow my cursor here, I can point them out. The results I'm going to be discussing are collaborative, but I just want to also highlight Yanju Go, who's also a postdoc here, has done a lot of work on the gamma jet tagged RAA result I'm going to show. And Jeff Ouellette, who's a recently graduated grad student here, did a lot of the Z plus H and dijet PLED results, you'll see. So team effort, everyone is doing a lot, but these two in particular are sort of the highlight of the talk. So without further ado, we're talking about jets in the QGP. This is a still taken from a video and also from this annual review article for new students, just showing the collision of these highly Lorentz contracted nuclei in several time steps. The important time steps for my purposes are time steps 2 and 3, which I've highlighted here, which is the initial collision, at which point you have your hard probes, your photon jet or your dijet pairs, your hard scatterings occur there. And then after some formation time, we move to time step 3. This formation time is on the order of a FM over C, less than that. But after that formation time, we have a fully formed Quark-Gluon Plasma, a state of deconfined quarks and gluons with unscreened color charges able to induce the physics effects that I'm going to go over. But specifically, we want to talk about the physics effects we call collectively jet quenching. So jet quenching, what is it? Here's a simple starter example. It's one of the first results out of the LHC from Atlas and heavy ions. And it's looking at fully reconstructed jets in collisions of lead nuclei in a centrality class 0 to 10%. The left-hand plot here. If I follow just the black circles, understanding, of course, that my x-axis is asymmetry. So the difference in momentum divided by the sum, it's a measure of relative jet imbalance. The black points show enhanced asymmetry relative to the white open circles, the PP data, or an appropriate Monte Carlo, Hygiene plus Pythia in this case. That's just to show that none of the detector effects from the addition of the large underlying event in lead-lead are really inducing this peak here in the black points when we compare it to the yellow or the open circles. So we have an enhancement of asymmetry. The basic signature of jet quenching here, one of the jets loses more energy than the other. So in the final state, it looks like there's a greater imbalance. You can also just see that looking at event displays, which is what the right-hand plot is. This is an unwrapped calorimeter event display in eta and phi space. Eta on the X here, phi on sort of the 3-dimensional Y, and then the Z axis being the transverse energy. We have a large deposition of energy in a very collimated eta phi space. This is a jet. And if we think, okay, my beams came in with no transverse momentum, therefore this transverse energy should have a balancing partner in phi, right? If we're conserving momentum, you don't really see a partner. You can squint and maybe drop a circle here where you see there's some elevated towers, but it's nothing near the collimated deposition of energy here. So that's jet quenching. This is an older measurement and an older event display. For one of our latest measurements, I really recommend you check out this new paper submitted to PRC recently. Okay, so that's jet quenching as it first came out of the LHC. An observation of this enhanced asymmetry. I'm going to talk about 3 modern studies our group have done, or more recent studies our group has done, that also explores jet quenching and tries to tackle specific, let's say, open questions in the study of jets in QGP. So the first result I'm going to discuss is gamma tagged jet spectra. I'm going to show this little cartoon where appropriate so people can keep track of which result is which. But here it's very simple. We're going to look at a photon in lead-lead events. This is a transverse view of my 2 large Lorentz contracted nuclei. We're just going to count the number of jets opposite the gamma tag, and we're going to compare with the inclusive RAA. Now, there's caveats to this comparison to the inclusive RAA, but the ultimate purpose of the comparison is to try and extract information of quark versus gluons. Do they interact differently with the medium? Do they have different effective color charges in the QGP? And so I'll explain this more as we get to it. The second measurement is going to be Z-tag jet fragmentation functions. Here, it's very similar. We have an electroweak boson that tags the initial hard scattering, lacking color charge, doesn't interact with the QGP. And we're just going to look opposite in hemisphere for its balancing color charge containing jet or carrying jet. And we're just going to count the hadrons associated with this final state jet. And this is going to give us something to compare to the models and make some concrete statements about medium response. By looking at the charged hadron collection associated with the jet opposite the Z and just comparing to models. And then the final result that I'm going to talk about is a search for quenching in P-lead using jet-tagged hadron spectra. So the measurement is very similar to others. We no longer have our electroweak boson opposite, but we do still have a tag object here, the tag jet. And we're just going to count hadrons. Both those in the near side of the jet tag and the away side. So that's one difference with the other measurements. So we're also going to be interested in the near side in this measurement. And again, this is in a search that I'll explain for quenching in P-lead given the observation of high PTB2. So those are the three measurements I'm going to discuss. There's many more. Please check out our public wiki if you aren't familiar with it, if you want to see more. So these results don't come from nowhere. They come from the LHC, specifically the Atlas detector at the LHC at CERN. This is an aerial view provided by CERN of the Swiss-French countryside outside of Geneva. And also if you follow the red line, which my cursor is currently going around in the image, this is the extent of the ring. It's 27 kilometers in circumference. And I've gone ahead and just highlighted the Atlas detector right here in the blue circle. This is also where CERN is. Atlas is right off site at CERN, which is quite nice. Of course, the actual detector is not at CERN above ground. It's 100 meters below ground, as are all of the other detectors. You can see ELISE, LHCb, and CMS in this cartoon on the right-hand side. The Atlas detector itself is a very complex machine, a series of interconnected subsystems. In the interiormost, we have tracking subdetectors. If you sort of squint here at the inside, these are surrounded by electromagnetic and hadronic calorimetry. And on the outermost, we have muon detectors, forward calorimetry, 0-degree calorimetry, etc. Now, we're going to use three different data sets here. Proton data, this is typically a reference, and it's collected mostly in 2017. Lead data for two of the results. We'll be looking at lead data collected in 2018, and then the P-lead data was collected in 2016 for the final result. The different objects and how they're reconstructed is detailed in the bulleted list. I'm not going to go through them except just to point out that jets are reconstructed using calorimetry only effectively here. Sometimes tracks are incorporated into the reconstruction, for example, in fake rejection, but they're not literally a part of the composite object. That's just calorimeter towers. So when we talk about jets, we're just talking about calorimetry. When we talk about the charged particles associated with jets, we're talking about the inner tracking detectors. So that preamble out of the way, result number one, gamma tag jet spectra. So this is not a new idea to take a colorless object produced at the tree level with the jet and to try and use that as your initial hard scattering proxy, so that you have a sense of the full amount that the jet has lost energy, rather than making a selection on the jet after the fact and incorporating in some sort of PT selection bias. So the left-hand plot here is an Atlas publication of the gamma jet measurement, comparing to three different models, Joule plus Pythia, hybrid, and BDMPSZ. This is just the lead data. There's no PP data. And what you can see is that we have something that peaks, let's say, this shoulder here at around 1, but it's really extended to much lower PT, XJ gamma being the ratio of the jet's PT with a gamma's PT, the balancing gamma's PT. So we have quite an extended collection of jets and central lead collisions here.
Wait, so you have some kind of like some block on the right side of your screen, and it's always blocking. Oh yeah, now it's okay now.
Okay, yeah. I think I know what that is.
Yeah.
Is this better? Can you see everything
No,
now?
no, now it's okay. Now it's okay. Yeah.
Okay. It's the Zoom window with the little videos was,
Yeah, yeah.
I guess,
Now,
somehow coming through.
now it's okay. Yeah.
Okay.
Thank you.
Apologies about that. Oh, I just finished summarizing the Peter, your hand is up. Is that to interrupt here, or
Well, hopefully not to interrupt, but to
just to ask a question?
to ask a question. Yeah. Yeah. So maybe if you're going to get to it, then just table this. But can you say a bit about actually the photon measurements? I mean, photons are colorless only to the degree you can suppress the fragmentation piece. So
yeah, that is true.
Do you have something about that? And so 2 questions: Atlas lead versus PP, and then Atlas versus CMS. How are we to think about these photon populations in terms of isolation and suppression of the fragmentation piece? I mean, it's clearly a complicated theoretical question how the fragmentation piece contributes, but what's the experimental way of thinking about this?
Yeah, so I'm not going to get to it later, so I'll just address it now. So your question is about fragmentation photons that, let's say, pass our isolation criteria that we use to try and suppress it. I think the answer from the experimental perspective is we just have a functional definition for this, and we try to handle it with purity corrections and things of that nature. But ultimately, modeling fragmentation photons is not something we can do. That has to be handled on the theory side when comparing to the data. I know that's not a satisfying answer, but I think we have a functional definition. We provide, all of the appropriate cuts we make, right? The isolation criteria, identification, etc. But at the end of the day, someone has to just model it, I think. And actually, when we get to the Z boson component of this talk, one of the nice things about the Z is you don't have to worry about that. There's no fragmentation Z contamination in our measurements, really.
Maybe I can just follow up briefly. So in PP, at least one has some Monte Carlos that maybe somewhat realistic and tested. Do you have any sense of how much you're suppressing the fragmentation piece with your isolation cuts in proton? That's a different story, I guess.
Depends on where you are in PT. I think at low PT it can be quite sizable. At high PT, your purity tends to get much better. I don't have a great answer here though.
Okay, that's cool. Yeah, but it's a satisfying answer because I don't know it's complicated, and it's what one does. I wasn't trying to trip you up here. I just wanted to if you had any kind of model studies or anything. But let's go on.
No, it's no. My answer is purely I think that it has to be handled on the theory side, and while we do our best to suppress and give as much information as possible, yeah, that is the situation. But okay, sorry, go ahead.
I was just going to ask, on the left hand, the Atlas plot are those data unfolded?
Yes, so that is actually a significant difference here. The Atlas side is unfolded. It's missing the PP points. That's on other plots. I just chose this one because I think it's a useful one. But the Atlas is fully unfolded. The CMS is not, which is why the PP has the smeared parenthetical. So the PP has been modified such that it's comparable to lead for detector effects, but it is not unfolded. So in order to compare to the theory, you would have to smear in the theory effectively on the right-hand side. Left-hand side's unfolded though. Okay, so a long tangent, but the 2 things to take away here is one, yes, there's an interpretive foible here, which is contamination from fragmentation photons produced effectively with a color charge, as Peter points out. So my simple picture of the colorless probe being a proxy for the initial hard scattering doesn't quite close, but okay, that's something for maybe theory to handle. And then the second thing is the left-hand measurement here, unfolded, Atlas gamma jet, perfectly comparable to theory as is. Right-hand side, not unfolded, but does illustrate the difference between the PP and the lead when we make them comparable within the detector's resolution effects, right? So what we observe when we compare the PP and the lead on the right-hand plot from CMS is a significant suppression of the more balanced pairs, the XJ gammas that would be closer to 1, right? There's this depletion in the lead. So this is a previous pair of gamma jet measurements from CMS and Atlas who have comparable kinematic reach here. So I want to motivate a new study, given that we already have done these studies. What is our new study? And to motivate it, we're going to look at quark jet fractions. This is using 3 different generators, Pythia, Sherpa, and Herwig. And we're just comparing open circles / open boxes / open crosses for inclusive jets, and then their closed counterparts for gamma-tagged jets. And if I just put a box here around the quark jet fraction for the inclusive jets, this is pretty well known, but nevertheless, just to repeat, it's mostly gluon jets, actually. Maybe as you go to higher PT, it gets to 50-50, but you're gluon dominated. And we have existing measurements looking at these populations of jets, notably this jet RAA that was published in 2019 from Atlas that shows these many centrality bins and long kinematic extent, right, from PT 100 to 1,000, a TeV effectively in central collisions. So what we want to do is say, hey, we have this measurement of an observable RAA, which I'll explain a little later if you're unfamiliar. And we also have these 2 systems with very different Quark-Gluon fraction. Can we construct a comparable observable in a gamma jet system that might exploit this difference in information and give us something new about the QGP? And I think the answer is yes, and it's why we did this analysis of gamma-tagged jet RAA. So again, my little cartoon is here to help me. Selected jet or gamma. We're constructing spectra from all jets opposite the gamma and azimuth. So I've just illustrated pi/2 here. You could have made a bunch of choices. We had control at pi/2, so we did it. We subtract off uncorrelated jets using a mixed event technique. This is where you match events by global characteristics, say event activity, a vertex position, the position of the hydrodynamic V2 event plane. And then once those events are matched by those global characteristics, you can do a statistical subtraction by just comparing the jets associated with the gamma in the event where it was produced with, if you were to pluck that gamma, put it in your other event and see what the correlation is there. You subtract off jets correlated with non-signal photons here via purity correction. This maybe gets at Peter's comment about fragmentation photons contaminating the spectra. You do try to handle this, but you don't have the nice quality of the Z where you're really guaranteed a perfect handling. It is ultimately something that needs to be modeled. You correct for detector effects with the 2D unfold, and then you just take a ratio of the spectra and the PP and the lead-lead to get at the RAA after scaling for some appropriate factors between lead-lead and PP for the number of binary collisions. So this is the analysis overview. I want to do a short example of the impact of spectral shape on RAA. So RAA, recall, is defined as the ratio of the, let's say, dN dPt jet in lead-lead divided by the cross-section in PP. But that cross-section is multiplied by this nuclear thickness factor, TAA. To give an example, TAA in our centralmost collisions is about a factor 25. And in peripheral, it starts to approach 1. So it's just taking into account the fact that in every lead-lead collision, you have some different probability of producing a hard scattering on a per minimum bias basis. So this is a toy spectra that I've generated to illustrate a property of the RAA. I've generated something that goes like PT to the 5th. It's just using T random 3. It's not actually modeling any properties of jet physics besides a rough spectral shape. And then I've also mocked up a fake jet quenching where we just reduce the jet PT by a constant fractional amount. I think I chose something like 0.6. That's a pretty unrealistic choice. Again, it's just a toy model to illustrate something. And what I'm going to illustrate is what happens to my toy RAA if we change this power law. So we change its shape while just keeping the actual mechanism of energy loss the same. On the right-hand side here, I've just changed my spectra to be power 3, which is a pretty dramatic change. It's quite large over the scale of 1 TeV along X here. However, what you see is that with the spectral change, while keeping the energy loss the same, you have a massive change in the final RAA. And so all this is meant to illustrate is that RAA is not just a measure of energy loss, it's a convolution of the energy loss with the spectral shape. And so that's going to be important later when we're interpreting the result. So here is the first part of the gamma-tagged jet RAA result. It's just the spectra. And it's the spectra and 3 centrality bins. The x-axis here goes from 50 to 150 in PT of the jet. The gamma tag starts at 50 GeV because we want this to be by construction a steeply falling spectra like our RAA, so we can do a final comparison to try and extract an effective color charge. There is the free centrality classes of lead, as I mentioned, and then importantly here, 2 PP distributions. There's the PP corresponding to the gamma jet, that's part of this analysis. That's the red circles. And then there are the PP points from the inclusive jet. These are gold stars here on the plot. And they are from the previously mentioned analysis published in 2019 for inclusive RAA. And what you can see already is if we take the ratio between my gamma tag spectrum and my inclusive spectrum in PP alone, there is a spectral shape difference. And so my previous example makes sense now. That's one thing you have to consider when you're comparing the RAAs between these two systems. And that's a big caveat in interpretation. This difference between the two is very modest compared to the example I showed you. We're talking about, I don't know, a factor 2 over 50 to 150. If I look at 0.05 to about 0.001 or so, let's say, in the last bin, nonetheless, it matters for interpretation. So that's one point.
This ratio is for PP or lead?
Yeah, this is just the PP ratio.
This is just PP ratio, okay. Yeah.
This is just telling you right out the gate, you have a spectral shape difference that has to be taken into account.
Okay, yeah.
So that's our first interpretive bugbear. But ignoring that for a moment, we can just go ahead and take the RAA right away from what you saw in the previous plot. Keeping in mind that there is a spectral shape difference that's going to matter for our interpretation, we do see an RAA in 0 to 10% gamma jet events. So that's the purple box here. We see something that's at about 0.6, and it's at about 0.6 across our full PT range. Now, in comparison, if we look at the red open circles for our inclusive jet RAA, this is, I don't want to say more suppressed because I just went over how RAA isn't purely suppression. However, we see a lower RAA, so something from 0.4 to about 0.5 in the PT range where it's plotted. So we observe a substantial difference in the RAA here. Now, interpretive caveats. I've already gone over that there is a spectral shape difference. That spectral shape difference, I think, goes against the current difference you see here between these two. In other words, it would make this gap larger. However, it would make the gap larger on about the same scale as we already see the gap. So the important thing to say there is the effect of the spectral difference is about the same in magnitude as the difference we see. Now, there's a second component, which is isospin can have an impact on the gamma jet production in lead. And I think it's the opposite sign effect. But once again, it actually has a magnitude on this measurement about the same as the gap difference. So while it's easy to look at this and maybe immediately want to say, okay, we've done it. We've shown that there's a different effective color charge between the quarks and the gluons. Not quite there yet. These are two very important interpretive caveats that need to be taken into account because both of them have magnitudes comparable with the size of the effect. So don't write home that this is, proof that quarks and gluons quench different in the medium yet. Going to paper, we hope to demonstrate that more thoroughly. However, it's a very intriguing first look at this data, and we do see what we would have expected to see had all things been held equal. Quarks appear slightly less suppressed than the gluons. That's the naive interpretation. So we can compare our gamma tagged RAA and then the ratio between the gamma tagged RAA and inclusive jets to different models. There's a whole host of models here. I'm not going to go into the details too much between the models because there's a global story that's maybe more useful to talk about right now. So the left-handmost plot, this is the RAA of the gamma tag jets. This plot is the RAA of the inclusive jets that's been out much longer. And then the rightmost plot, this is the ratio of the two with the gamma jet RAA in the numerator. So you should expect this to be above 1 when you think about the previous plot I showed. And then if you look at the models and you compare them panel by panel, what you're going to find is that the inclusive jets actually, all of the models are more or less centered on. I don't think that's surprising. Inclusive jets have been out for a while. And models have been comparing to inclusive RAs for a very long time. So if there's any internal knobs that could be turned there to get the data right, it would have happened already. However, assuming that the inclusive jet knobs are fixed, we can then look at the gamma tag jets, and what we find is that the models generally undershoot this value. There is some wiggle room in the case of, say, sqrt. The large yellow band corresponds to an uncertainty on the G parameter here, the range 1.8 to 2.2. So they have a large band and they're compatible with the gamma tag data because of that band. But ultimately, I think you can tell the centroid undershoots and most of the theories undershoot. And as a result, they undershoot the double ratio. That's the global story of model comparisons to the gamma tag jet RAA as it exists. So that concludes discussion of gamma tag jet spectra as a tool for understanding Quark-Gluon differences in the QGP. I don't know if anyone has any questions before I can just keep going, because the two results upcoming are related. Hey, Peter.
Yeah, actually, could I ask a question? We go back, please, to the where you showed the difference in recoil jet flavor for the
right here,
or the jet flavor. No,
well, it's not RicoJet. It's true.
I'm sorry. Yeah. Sorry.
No, no worries. No worries.
Somewhere else. Yeah. So you know what I'm thinking about. So the quark jet fraction. Yeah. So let's see. So you have Pythia, Sherpa, and Herwig, and that's all great. I mean, that's what we can do. But how exactly do you define this quark jet fraction? And kind of in QCD, it's not really a precise thing. You know, if I have a quark and it rapidly radiates a gluon, is that a quark jet, a gluon jet, some mixture? How exactly do you define this, and kind of how precisely should we understand this?
Yeah, so there's a well-defined answer, which is in the experiments we define this as was there a hard radiated parton in the cone of the jet? Effectively, it is an area definition. I think at the end of the day, we don't go through the tree necessarily of that Pythia spits out. I don't know if you've ever looked at that. So it's an effective geometric definition. Now that is maybe unsatisfying because, as you point out, okay, at a tree level, I might have a photon jet with a quark, and then at some time later, there is a hard radiation or some other thing, a gluon radiation. Ambiguities like that complicate the picture. But I think ultimately we just have to sort of pick an effective definition here, like the one I said, and hope that maps on to the truth quark or truth gluon content of the physics we want to extract at the end. I don't know if that quite answers.
Could I phrase this as a quark initiated or gluon initiated jet, whatever its fate may be? Is that the right way to think about it?
I think that's correct. Yeah, I think you should think of it as initiated.
Yeah.
I mean, there's the annoying caveat, which is like as soon as it starts radiating, right? It in the medium, right? It's like they become each other, right? It just starts radiating gluons, right? So that's why I said effective color charge. That there's an effective color charge between something initiated as a quark or initiated as a gluon, because that becomes ambiguous in the QGP very quickly. Yeah, but I think initiated.
Well, that's fine. That's your answer's clear, and it's what we can do collectively. Just want to point out at Rick, there was a result of quark matter from STAR where there's a gamma and pi zero triggered recoil jets that find no difference. I think it's in contrast to what you're reporting. I don't want to hijack your talk here, but different kinematics, different, many differences. But this Quark-Gluon thing, I think, also is relevant there. Do you have a comment on that?
I don't have a comment on the differences, because I think, as I pointed out or tried to point out, there's a lot of caveats in the observed difference between the two, right? It could be the spectra difference, and that changes with center of mass energy, right? The power law or whatever. that can change with center of mass energy. You have a steeper spectra at RIC, I believe, right, relative to the LHC.
By far.
Yeah, so I don't have a comment on those observed differences yet, especially because there's a lot of caveats into getting a Quark-Gluon effective charge out of this. So yeah, I don't know that they're comparable yet.
I think, Peter, I think maybe we should focus on his talk first, okay?
Well, we can
other as well, yeah.
I'm happy to discuss, but yeah.
We can come back later, yeah.
Okay, well, let's keep moving with the Z-tag jet fragmentation. So Z-tag jet fragmentation is also not a new idea, or looking at fragments opposite a colorless tag like a gamma, which is shown in this Atlas study here. These are not new ideas. This is a measurement of jet fragments within the QGP. Modified DZ is a ratio of lead to PP, and Z is the fraction of the jet's energy that a particular fragment takes. And what we observe in the ratio between the two is an excess in lead of soft fragments, a depletion of these intermediary fragments, and a hint of an enhancement at high PT, although as you can see, if I were to average over these two boxes, maybe it would be 10% or so, 15%, I don't know. But that is what we observe. Now, one question you can ask here, because this is a gamma tagged selection, it also includes a jet selection, right? Jets here that go into this fragmentation go from 63 to 144. That's our PT range. So you can ask the question, can we get a fragmentation modification without this selection bias? Because that jet you are selecting on is ultimately quenched. And while this is very far from the PT of the gamma, it's very possible that you could have gamma partner jets that are quenched below that threshold. So in the Z-tag jet fragmentation analysis, we tried to structure this such that that quenching bias wouldn't come in. So we selected on events with a high PTZ. This is done using muons or electrons reconstructed with opposite sign charge and existing within a mass window of roughly 20 JeV around the Z mass, so 70 to 110, give or take. We look at the charge hadron yields from all tracks opposite to Z and azimuth. So this is 3 pi over 4 in this case, that's the selection. You correct this for detector inefficiencies modeled in your Monte Carlo. Subtract off uncorrelated tracks using mixed event techniques, correct for detector effects with an unfold, and then take a ratio of the yields in both systems on a per Z basis, so no longer involving TAA at all to get at the IAA. So there's a few different results here I want to talk about. The first is the angular correlation, the delta phi HZ. So this is if I have my Z boson, if you follow my cursor, and I look at the charge hadrons opposite it. Delta phi HZ is this angle in azimuth, if you can imagine my circle subtending or my cursor subtending an angle. And when we look at this, we can look at it in 2 PT charge selections. So 2 to 4 on the left-hand column, greater than 4 JeV in the right-hand column. You observe a suppression of the the far angle, or roughly pi-ish, let's say, delta phi HZ. For PT greater than 4, that suppression is not so pronounced in the intermediary bin. I actually like this observation because it's consistent with other measurements that I've been involved in the past, like old missing PT measurements for CMS, where we frequently saw that actually like 2 to 4 was sort of a crossover point where you maybe no longer saw quite as much suppression. And then when you got below 2, you would start to see the enhancement again. So this is sort of a crossing point in my mind. It's nice to see this confirmed again, even if it's just sort of an idle qualitative confirmation. But that is more or less the physics here. You see something like a suppression in the high PT fragments in the window that would be associated with a jet opposite the Z. The intermediary fragments are less suppressed. Of course, we can quantify this on a PT basis on the x-axis, but before we get to the IAA, I'm just going to flash the spectrum quickly here. You can't extract physics from it, but it does illustrate the binning, which is we have 3 centrality classes, 0 to 10, 10 to 30, 30 to 80, and 3 PTZ classes. Each diagonal, if you follow my cursor here, is scaled by another factor 10, and they correspond to each PTZ selection. So the lowest diagonal PT of our Z is selected 15 to 30, 30 to 60, greater than 60. So there's our spectra. Let's construct our IAA. The IAA, again, it's related to the RAA, but it's particles per Z in lead divided by particles per Z in PP, because the Z is a colorless object. And also, very nicely, it doesn't have this fragmentation photon issue that we discussed in the last result. And we also observe it's unmodified experimentally. This is a very solid analog to the RAA, doing something on a per Z basis. And when we do this, if I just focus on the top panel, which is PTZ greater than 60, I'm going to ignore the other two panels, but the story is the same. We see a global suppression for the hardest fragments, PT greater than 4 in these first few points, up to a PTs of 60 or so at these last few points. A global suppression, roughly ordered in centrality. You're going to see that the peripheral and semi-central swap places in a few points, but mostly ordered by centrality. Centralmost is always the most suppressed. And then we see a corresponding excess of low PT particles. Once we go below 4 JeV, we hit maybe this crossing region I tried to highlight for 2 to 4. And then we see a larger excess here, although its deviancy from 1 is our ability to make a strong statement about the deviation from 1 is limited by the statistical error bars. This is interpreted as the medium interactions or the quenching effects of the medium interactions are attenuating the energy and redistributing it to the softer fragments. Again, maybe something expected once you see jet quenching, but good to confirm. So we have a theory comparison, and this is mostly where I can make a comment about medium response. So far, in my mind, a lot of the discussion of medium response has to occur in a model-dependent way. I don't know that we have very solid model independent ways to talk about medium response yet. But what I can do is talk about the hybrid model here, which is plotted in comparison with our data in 2 ways. It's with a wake structure and without a wake structure, right? The solid boxes for red, purple, and blue, this is with a wake structure. And then we have these dashed boxes for without a wake structure. And what you find is that you can get the high PT behavior without a wake just fine. And I think that makes sense. Your medium interactions tend to hit your hardest fragments, make them softer. But where the wake is necessary is in describing the low PT behavior. Getting the soft particle excess doesn't really happen when you don't have the wake implemented, the medium response implemented. However, when you have the medium response implemented, you see that lost energy to the medium is redistributed with softer particles, and redistributed to softer particles within that delta phi window we described, such that you get, when you add the wake to the hybrid model, you now get this behavior qualitatively. I'm not going to say quantitatively, it agrees great with the data because there's clearly a few points it's missing, but you do get high PT suppression, low PT excess. So in that sense, we can make a statement in a model dependent way. The hybrid model, which combines this ADS-CFT inspired strong coupling based energy loss with the perturbative vacuum-like evolution of its fragments otherwise. In this case, having medium response, having a wake describes the data best. I want to make one more point here in a comparison with CMS. If you recall, when I started talking about this, I made a big point about jet selections and a possibility of bias when you know your jets are quenched when you select on them. So this is comparing CMS PT gamma with Atlas PTZ. There's, of course, the difference of fragmentation photons in the gamma channel, but I think the more important difference here is actually the jet selection. I think selecting on a PT jet greater than 30 here by CMS has artificially is the wrong word because it's just a choice. But what it does mean is that you're missing part of the story. And part of that story is jets that are quenched below the 30 JeV threshold that could be contributing an even greater sort of quenching effect here. Like we see a greater suppression when we have no jet selection versus when we do. So something to keep in mind when you're looking at these is that jet selection is important and can sometimes hide part of the story. To get a full picture, you have to consider it with that selection without. But that completes the Z fragment discussion. And then the last thing I want to talk about here before doing a short aside about S-Phoenix is jet-tagged hadron spectra in PLED. So this is a search for quenching that I need to motivate. So the left-hand side is a recent plot by Atlas of jet V2. And it shows persistent jet V2 to very high PT in jets in multiple centralities. In 0 to 5%, you don't really have a pronounced V2. However, in 5 to 10% and in 20 to 40%, I think it's clear that you do have this persistent V2. Now, this is generally understood as a product of differential jet energy loss in lead-lead. If I have two jets going through the medium with different path lengths, it's very likely that that is going to lose energy, or those two jets are going to lose energy in different ways, and therefore induce the elliptical V2-like signature, right? One jet is going to have lost more energy than the other. There's an asymmetry. That understanding, of course, requires that there be jet quenching present, period. And recently, Atlas has also provided a measurement, and this is actually from someone in our group as well, although he wasn't in the photo at the start, Kurt Hill. We have a persistent V2 to high PT and PLED. We have this despite the fact that there's no existing observations of quenching in PLED, which means that there's no existing mechanistic explanation for this persistent V2 to high PT, right? We'd need to see quenching for differential jet energy loss to be explanatory here. So one,
what is your PTA means? What is your PTA associated particle?
Sorry, say it again. Oh, PTA, yeah, associated particle, sorry.
Okay, this is an associated particle for a given jet trigger value, right?
Yes, it's jet with particles, but you can see it's going to very high PT in those particles as well.
Yeah. Okay. Yeah. So anyway, but this is not just you look at the anisotropy of high PD jet.
No. It's not just jets.
Yeah.
The left-hand plot is just jet V2, but the right-hand plot is not. Sorry, they're different studies. They're related to the same physics though, and I think they're ultimately signatures of the same thing.
Sorry, Chris, I missed it. What's the observable in the right-hand plot?
It is the V2 of high PT jets with associated particles in an event going to high PT. On the x-axis, you can see the PT associated goes to, I don't know, 100 JeV there, but maybe the bins stop at 20 to 30.
So what do you mean by PT? So I'm slow here. What do you mean by PT associated?
It is a V2 in events with high PT jets with a between the jets and all the particles in the event bin in the associated particles. The x-axis is like the PT of the particles. That's what PTA was referring to.
So it's a kind of a two particle V2 between an IPT particle and a jet?
Yeah.
Okay, I see. So you take a hadron and a jet and you look at their two body correlation, is that correct?
Mm-hmm.
And you extract a V2.
Mm-hmm.
Got it. Thank you.
Okay. Importantly in PLED. So left-hand side, lead, persistent high PT V2. Right-hand side, PLED, persistent high PT V2, without any observation of quenching. One question you can ask is, excuse me. One question you can ask is, okay, I see the signature. I haven't seen quenching yet. Maybe I didn't look hard enough. Maybe I need another search for quenching. And of course, we're not the only people who've searched for quenching, although I'm going to show you that search in a second. Elise has also done a quenching search. This is QPLED. You should think of it as very similar to RPLED. There's some nuances in the definition, but effectively it's a ratio between production of particles in PLED with their production in PP. The x-axis is the PT of these particles. You can see that you run out of, say, statistics with Elise as you go to the highest PT, but you do have an answer that suggests that there is no suppression on, say, a 5 to 10% level. That's what I would say based on the statistical errors and the systematic bars that you see in the ratio panel in the bottom. So from these centrality binned charged particle QPLED, you can say, okay, I've ruled out quenching effects on this order. We're going to do a similar study using a larger high PT sample with Atlas, but adopting the QPLED approach of using the ZDC to define centrality in PLED to avoid biases associated with dijet production, biasing mid-rapidity activity categories when the overall activity of an event is very low. However, we're going to do this on a per jet tag basis, so we'll have no errors associated with the determination of end call for these different PLED centrality classes. So this is the analysis overview. You have jet tagged events. The jet tag can be 30 JeV or 60 JeV. And we're going to construct charged hadron yields via tracks on the near or the away side of the tag jet. We're going to look at both sides this time, not just the away side. We're going to look at delta 5 pi over 8, so near the tag jet or opposite side 7 pi over 8. Correcting for all the detectors inefficiencies and fake rates, subtracting uncorrelated tracks using mixed event techniques matched by ZDC detector activity. We're going to correct for detector effects with a 2D unfold. This is an unfold in the jet's proton or the jet's transverse momentum and the track transverse momentum. So it's a 2-component unfold. Then finally, we're going to take the ratio of the spectra in PP and PLED to get an IPLED. So we define centrality with the ZDC here. This is the distribution of the energy deposited in the ZDC in the lead going direction in this case. You can see that there's a bunch of different percentile lines. The individual dash percentile lines correspond to 10%. However, we've gone with a coarser 20 percentile binning, and I've tried to highlight that with this red text on the plot. The reason this is not subject to the same biases in centrality determination when your events have low activity that say mid-rapidity determinants do is it's looking at spectator neutrons after nuclear breakup way down the beam pipe. None of the activity we observe has anything to do with what's happening physically in the detector besides how many nucleons broke up. That is not necessarily true of, say, centrality determinations using forward calorimetry, right? This is a different thing. So we're going to report results using centrality classes determined using the ZDC in bins of 20% centrality. This is just the jet tag charge spectra. Much like when I showed you the Z spectra before, it's difficult to extract any physics from this. We have to take a ratio. But again, just want to highlight, we're looking at two delta jet charge hadron, delta phi jet charge hadron selections, a near side or pi over 8 and a 7 pi over 8 or away side. The IP LED is shown here. So that's the spectra shown in the previous slide, but just taking ratios with PP for the different PLED centrality classes. Going from left to right, we have ZDC selection centralmost 0 to 20%, intermediate 40 to 60%, and peripheralmost 80 to 100%. The top panel is the away side. So you should think I have my tag jet, what's over here, versus I have my tag jet on the bottom panel, the near side, what's in here. And what we observe is basically bupkis at high PT. We don't really see any deviations from unity in the away side. In the near side, we do see a modest excess, but A, that's not a quenching signature, and B, as you'll see, it's perfectly modeled in Monte Carlo without any quenching or hydrodynamic flow for that matter. So this is the result. We don't see any quenching that could explain the high PTV2. And I'll give an example of why that's the case in a moment.
The difference between up panel and low panel?
Can you say that again? I missed what
What's
you
the
said.
difference between up and low panel?
Yeah, sorry. Upper panel. So if this is my tag jet, and then this is, say, my away side jet, the upper panel is the tracks associated with the away side jet. Bottom panel is, or bottom row of panels is the near side jet.
Oh, it's just away side, near side.
Exactly. Yeah. I have these little arrows here, but they can get lost in all the text. So yeah,
The
delta
upper panel
7.
is, the upper panel is same side, the low panel is.
No, sorry. Upper panel's away side from my tag jet.
Yeah, it looks okay. Thank you.
Yep. And then again, column wise is just different activity selections, which reminds me, I should have noted this, the bottom panel, even though we see an excess, already said that's not consistent with quenching. Another notable thing is it's relatively constant across the centralities, right? There's no centrality dependent effect observable there. So we didn't quite understand the near side excess, but we wanted to try and rule out that it was, let's say, quenching physics, or a more conservative statement would be not explainable by quenching physics alone. You can explain it with other things. And so what we did here is we compared to Angentor, which is a model without quenching effects, and specifically Angentor without string shoving turned on. So there should be no collectivity effects either. And what we found is that when we run Angentor, we can run it with different PDF selections, different jet selections, etc. We do basically see the near side excess in the data. That's the left-hand plot panel here. So just quickly flashing back, you should think of it as being the bottom set of panels here. That's what's being plotted on the left side here. So the pi less than pi over 8 selection. We get this excess without really making any selections at all. We're going through turning off different, turning different nodes in Pythia to try and figure out what exactly causes what we observe. But as of right now, we don't know. We're just confident it's not quenching effects or quenching physics. You don't need any of that to get this distribution. And you see something similar in the 7 pi over 8 selection. Of course, that was less pressing to explain because we saw something comparable with Unity. So why is that a magnitude of quenching important? I'm going to return to the paper where I showed you this high PTV2 in PLED. So this is an attempt at modeling high PTV2 in PLED. There's 2 different QGP droplet sizes here, size A and size B. The choices are not very important. The important thing is it's just attempting to model a QGP droplet in PLED interacting with jets such that we would produce a high PTV2. And what they found is, yeah, they can get a high PTV2. If I look at these dashed lines, it's maybe not exactly in line with the data, but okay, it's a V2 that is comparable in magnitude. But you would have a corresponding suppression if I then look at the right-hand side and I look at the RP lead, that's enormous. I mean, this is basically what we see in central lead as a reminder in a lot of ways. So doing a simultaneous constraint of these things really illustrates the problem of high PTV2 in PLED. We don't, I think, currently understand it. Certainly not in any models I've seen. So you can ask the question, does quenching have to have the signature? Maybe it doesn't. Maybe quenching can be closer to 1 here, but still produce this effect. And therefore we maintain our differential jet energy loss explanation for high PTV2 and lead. Or is our understanding of high PTV2 and lead wrong? Is there another mechanism at play besides differential energy loss? That's sort of the question I want to pose here. And then this final plot I'll show is a cute one. It's just showing the overlaid central lead energy loss of ZH fragments compared to this dijet tagged one. It's a little silly because it's comparing a lead quenching effect to PLED. But from the previous plot, I tried to illustrate that, yes, you really do need a lot of quenching here. So maybe it's less silly than it seems. Peter, real quick, if you want to.
Yeah, just coming back to your the first part, kind of tying together the first part of your talk, and this will go back to the previous slide, where you made the point that suppression doesn't equal energy loss. It's connected by the shape of the spectrum.
That's true.
Can you put a number to the shift in the jet spectrum needed to get the V2? The V2 is just a ratio of yields, right? So if you assume the same shape spectrum, can you put a number to the shift of the spectrum?
Yeah, Peter, can I suggest you just wait a little bit because let Chris finish the talk and we'll.
Oh yeah, we'll talk right at the end here, Peter. I'm sorry. Yeah. I saw your hand. Okay, well, we'll talk about it in a second. I'm going to speed through some things quick. That was the last measurement. And just a real quick other things that we're doing right now as a group related to these 3 measurements, but also doing new technology. So one thing we're doing right now is the S-Phoenix detector. which is a dedicated jet physics experiment at RIC, other physics as well, but I'm mostly excited about the jets. It has full acceptance out to eta of 1.1, 2 pi and azimuth, highly granular electromagnetic calorimetry, comparable to CMS even, they're great. Lead tungstate crystal ecal, comparable granularity at S-Phoenix, hadronic calorimetry and inner and outer H-cal, unbiased jet triggering and proton-proton collisions. I'm working on the trigger boards right now, so maybe put some cross fingers next to that bullet point, but okay. And then a large data taking rate for maximizing the luminosity in AA collisions. This is going to give us some pretty fun capabilities. So these are just 2 projection examples for the photon jet and the jet ZG, which is a substructure observable I won't explain here, or at least not the exact meaning, but you should think of it as an observable measuring the pronginess of jets, or how much a jet is holding its energy in, say, a subcone within the jet compared to other subcones that you could pick. That is what you should think of ZG as, a measure of pronginess. So we have capacity to do both these things in S-Phoenix with our new detector, which is quite nice. Now, the detector doesn't spring fully formed. We have to build it. So here's just what we do right now at University of Colorado is mostly do board testing, or at least that's what I did for a very long time. This is an ADC board for S-Phoenix here on the left-hand side, and our little test stand on the right-hand side, where we put these boards through their paces, make sure that the pedestal, the gain, etc., all works as we expect it. Each of these boards is going to have a 64 channel input, so they better work exactly the way we want, or we're going to have a lot of very confusing data and not a lot of jets at the end of the day. We are also working on building, or not building, but testing calorimeter tiles. The left-hand side, this is a photograph of a calorimeter tile and also an LED scan we've done of these tiles to make sure that the light response is as expected and there's no breaks in that fiber optic cable, which you can see here, the thin line here that shows the largest light values. That's the fiber optic cable, wave guiding cable, and it comes out here at the end to an SIPM for readout. This is a H-cal tile. The right-hand side here, recently S-Phoenix added an event plane detector, a forward event plane detector, which will help us in determining the event plane of given lead-lead events. Or sorry, I keep saying lead-lead because of the LHC, gold at RIC. These tiles are being tested using a very similar LED scan, like so. For the SCPD. This is another one of our many responsibilities at the University of Colorado. So that's building the S-Phoenix detector. And then the last thing I want to leave you with is some technology I'm working on for doing multi-jet analysis. This is maybe very ambitious, but what I want you to consider is when we talked about that gamma-tagged jet RAA, we were considering configurations like the left-hand side, where we have a gamma most likely produced with a quark, not necessarily with a quark, but most likely produced with a quark, with a tree level diagram that looks like this. We can consider a multi-jet event instead, where in addition to my gamma and my quark, I have some hard radiated gluon, right? I have a multi-jet event, I have a quark and a gluon, most likely in the same event. And I want to ask, can I construct an observable that might be sensitive to an effective color factor between these 2 jets? And also, can I study them in a manner akin to what the dipole folks like to talk about, where we talk about interjet quantities and thinking about, can the medium resolve these as distinct? At what scale does it resolve them distinct, etc. So the hard technological question, though, is what is the algorithm for multi-jet mixing? I think I have an answer to that question. I'm not going to go over the exact algorithm because it's a little boring, but this is just a toy multi-jet spectra to show you that we can get closure if we think about it. So I've just randomly populated events with 80 to 100 GeV gammas. There's leading and subleading jets opposite that photon. So it's not leading in the sense that it's the highest PT object, it's the leading balancing jet of the gamma. And you can see this bump here is just because the 80 to 100 GeV selection pulls this distribution up. My subleading jets are typically lower than my leading jet by definition. But then I populate with a huge number of fake jets. That's what the red band is. Treating all of the jets as equivalent at an analysis level, since at an analysis level, I don't know what's real and what's fake. I just know that I have a collection of jets. Can I extract back some multi-jet observable? And this is the example. I think the answer is yes. I've constructed what I'm calling XJJ gamma, which is a multi-jet 4-vector sum. Take the transverse momentum and then take the ratio with the gamma PT. If you like, you should think of this as basically resumming to a tree level diagram for dijet configurations. In this example at least, I'm able to model the background exactly. So you can see in the ratio below that my signal plus background, except in the instance at 1 where I had it be constructed perfectly signal, my mixed event tracks it exactly, right? There is a caveat here, which is that these are not area extended objects. I made my jets effectively point like here, just for the toy. So there's complications to this method when you have a non-zero jet area. However, I think we can get back to the multi-jet physics, even with those complications. And so that's the last thing I wanted to leave you with before my little conclusion here. Thank you so much for listening. I went long, I'm sorry. But I hope you were able to take something out of this.
Okay, thank you very much, Chris. Yeah, this is really a lot of information. And I think, Peter, why don't you continue your question?
We can go back to.
Yeah, back to the UNIV. Yes, I just had your comparison there.
What am I doing? I'm sorry, I'm very confused. Here, right?
No, you had the.
Or do you want the spectral shape example?
Yeah.
Okay.
Right. Can you? Oops. Oh, lost it again.
Right here, right? Spectral shape example.
Yeah. Well, no, actually, I wanted the PLED, but let me just ask my question. Can you, the PLED V2, it's just the ratio of yield. What is the effective horizontal shift that corresponds to a V2? In other words, in the spirit of this diagram, what is the, if it were all energy loss, what is the magnitude of that energy loss? And likewise, part B of the question is you see no finite effect, but you have uncertainties. You understand the uncertainties. What is the limit that your inclusive puts on the energy loss and the inclusive measurements?
Huh. So those are good questions that I don't have great answers to, but I do have answers. On the energy loss, I want to say that given the spectral shape, well, okay, here's the answer I can give, which is that as we go to looking at this for paper, right? So this is a preliminary still. As we go to paper, answering questions like, for example, about the spectral shape and the energy loss is part of what we're going to do. I don't know the exact value. I think my recollection is that 20% energy loss will give you roughly what the central lead-lead RAA is, but I don't know how to translate that to the PLED here. So I'm not saying 20% energy loss is responsible here, but that's my memory for central lead-lead, given that spectral shape, is what kind of average energy loss you would see. What was your second question, Peter? It was about.
Well, then if you go to the inclusives where you showed no effect with an uncertainty.
But what was the limit we're placing? Yeah, that is another.
If this is a bugaboo about our field, and I'm as responsible as anybody. We say we don't see anything, but then what? I think
we don't quantify it appropriately.
There's information here about how big would the effect have to be to not be consistent with the data.
In so much, well, okay. How big would it have to be inconsistent with the data is not something I can answer, but should be something that we answer going to paper off the top of my head. What I can say is that if I were to characterize the Elise one as, say, 10% level, which I think is a reasonable eyeball, admittedly an eyeball, I think we're approaching percent level, but that's not a percent level limit on quenching at all. That's a percent level limit on the IP lead or QP lead, right? So we'd have to go through the whole rigmarole of taking the spectral shape and figuring out what the energy loss that would correspond to that is. I don't know the answer, unfortunately. But I would just try to phrase it in terms of, if we think of that at least centrality dependent QP lead as limiting things on the order of 5%, 10%, this is bringing us to 10% level, or sorry, percent level.
Let me just one more quick. So there is
Please.
another Alice measurement, a coincidence measurement, that actually does quantify the shift and sets limits at 400 MeV. This is for charge jets, 400 MeV at a 90% confidence level. So that's quite a, it's for, quite a stringent limit, and one can go beyond that. We can talk about that offline.
No, can you remind me? I think I know the measurement you're talking about. Can you remind me though? Is that centrality bend?
That's hadron jet, and so it's self-normalized. You don't have to, or it's absolutely normalized. You don't have to get a Glauber factor. And
sure,
so indeed,
no Glauber factor. I was thinking merely centrality.
We look at high multiplicity P lead versus minimum bias P lead. So
okay, you do look at activity, because that's the other thing I would say is making sure we're looking at these in activity differential ways is important.
And likewise, one can, for these, absolutely normalized observables, you can also do them proton-proton. There's a result there as well.
Okay.
So I think there's several things to compare to, but I agree with your essential point. One should convert it all into some effective energy shift. You need some assumptions, but that's the way to compare. Okay, I'll let someone else ask.
Just as one last comment to tack on there, though, I think the wealth of measurements we have at this point, even if we don't have perfect quantification of how little energy loss it implies everywhere, does, I think, highlight the importance of understanding the high PTV2.
Mhm.
Right? We have everywhere non-observations of quenching, no observation of quenching. We have high PTV2. We have this explanation for it that doesn't seem consistent with that non-observation. So that would be maybe more the thing I'd want to highlight.
Yeah.
Okay. Yeah. Matish. Hi, Matish, you still there?
Yeah. I'm sorry, I was away. So yeah, Peter was quicker with that question, but essentially, yes, the V2, one can see it as a event plane dependent RAA, right? And then one has to check whether what we get with energy shifts. I think one should also do that in lead actually, and maybe even with Z jets, not just the P lead measurements. On a side note, I mean, Shinyan is here, but I've heard theorists who claim that this energy shifting is not the real quantification. I mean, it's not a quantity that is in any way calculable. I mean, one can Monte Carlo it, but that's not really well posed question as how much energy actually jet loses. But I set it aside, and then so I'm really interested in knowing in really understanding what is the shift when you take the V2s, especially in P-lead collisions. But I have a question. So I connected late. Did you show the Z boson V2?
No, I'm sorry.
Is it 0, even if you don't show it?
I think so.
Well, you see, my point is it should be. Okay, so let's fix it at 0 for the purpose of discussion. And then, but then if you go to your plots, my interest is essentially you see some excess of correlated yield to a jet, which later on is called wake in those models, right?
Yes, yeah, the soft component, yes.
Right.
Yeah.
So my question is that correlated with event plane? Because one can, to create a wake, you actually also need some material to create the wake, right?
Yeah.
And in different direction or orientation of your Z jet pair, you have more or less of that material to create the jet. So I think it would be, first of all, interesting if the hybrid model is sensitive to the event plane, or let's call it eccentricity, initial eccentricity. And if I know you don't have enough data judging from the error bars now, but I think it's a great future measurement to essentially do that azimutally dependent, and then to see whether wake is something correlated or uncorrelated or in what way, let's call it like this, correlated to the event plane. Because it seems to be, I mean, we might have also some either experimental issue of how we analyze jets, and this could be slight energy balance or energy scale problem. If I set that aside and claim we do everything correctly, we still might be looking at some essentially event plane orientation with relation to the wake or the signal of the wake.
Yeah, that's a really interesting point. And it's one of the things we've sort of spitballed when we talk about high PTV2, which is specifically, well, there's more stuff in one direction versus another for the jet to sort of equalize its color charge to a colorless configuration in the final state, right? There's more stuff for it to work with. So that's definitely something we've spitballed. I can't give very quantitative answers except to say,
well, one thing it would be interesting to ask the hybrid guys if I mean how their curves look versus eccentricity, right?
I think it absolutely is a question for modeling. I think that's the right way to think about it. And the reason I say that is you pointed out, okay, our Z plus H, maybe we're limited in statistics, but we could do a future analysis. Well, the LHC's total delivered luminosity, I think, is supposed to be 10 inverse nanobarns. And if you saw my plot, we're already at about 2. So you're only going to see those errors come down a factor √5.
Well, cross fingers for run 5 and run 6 to answer those questions, where you get an additional order of magnitude. Coming also to one of the observations that Peter pointed to, the hadron jet analysis. There, I also think, Peter, we have to, there's a bit of homework on our end also. We need to understand how the hadron V2 does come into the game, right? Because it's not so innocent to trigger on a hadron that has already intrinsic V2, right? It's different than with the Z boson.
For the record, that we kind of do our best to work that into the systematics. We take the measured hadron V2 and we take the lower bound, the upper bound, and say how would that contribute to the effects we see. I think that's more significant for the central lead where the backgrounds can be very strongly biased if you actually have even a modest V2.
So I meant the lead. Yeah, I meant the lead.
Yeah, no, but also PLED. I mean, it's we're after precision here. We should all agree we're after precision, and so these effects absolutely have to take into account. The alternative, of course, is to do a photon, and Z eventually. So also these kind of semi-inclusives, which Chris, I'd like to discuss that with you afterward.
Then we will deal with the photon V2.
Yeah.
Precision.
But right, but absolutely, one has to account for this, and I think we have to put everything together and see whether I agree absolutely with your central point. This V2 is really a deep puzzle. I don't have a magic bullet here, but it's very interesting.
Yeah, well, I mean, I think maybe if you can do measurement of look at the azimuthal anisotropy of, for example, of your direct photon, for example, high PD direct photon in PA, that will be independent measurement whether there is actually, whether V2 is caused by initial state interaction, because we know that there are theory calculations that does not need jet quenching to produce anisotropy. Just all they need is some kind of initial correlation there.
Well, can I
That's
maybe
why I also asked about the Z boson V2.
Yeah, photon might be more doable statistically than Z, but then you have to worry about the fragmentation. I'd have to think about both those approaches, but they are. I'd have to think about it. I mean, what I want to glom on
for the Z, you could split your sample in 2 and call it in out of plane, and it will still be probably not conclusive with the statistics.
Yeah. So
I got to run. Xinyan, sorry, one remark. Christopher, thank you for a very nice talk.
Oh, no problem.
So in this case, you don't necessarily have to have the spectrum shift in order to have the V2. All you have to do is you don't have to have energy loss to have V2, especially in PA. in PA interaction.
Well, what I wanted to glom onto with that comment is I'm not sure though. I mean, I agree with you that there's mechanisms to do this outside of differential jet energy loss. But what I think is missing is a coherent and complete view of these mechanisms that explains both systems. And part of that is it's a new observation. People haven't necessarily put a lot of time into thinking about it.
Absolutely, that kind of initial state, correlation probably will not be present or will not be the dominant mechanism for V2 anymore in heavy ion interaction.
Yeah. What I'd really like to see though is that I'd like to see the transition and the relative magnitudes and how these things interplay, and I'm just not sure I've seen that yet.
There is as I suggest that all you can do is just look at the direct photon.
Yeah. No, I have made a note of that.
Look at the direct photon. We know the photon does not have loss energy, and if you have final V2, that will directly answer the question for you.
So
no, I think that's a good idea.
I just want to ask this question, Chris. So I'm not a V2 guy. I've never done a V2 analysis in my life. I've done a lot of things, but not V2. I always get nervous about event plane biases. I know, very many brilliant people have, come up with, n different methods to assess the bias and to minimize it. But we're looking at jets and dijets. There's always a danger. Now, Atlas and CMS have wonderfully large longitudinal coverage, and you can go far away, and et cetera. But dijets are back to back, and they can be anywhere in eta. So, do you see any issues there, or do you think that's a settled issue?
Well, I mean, this is a very striking observation. So I don't want to say anything is settled. I think you have to look at everything, right? Even if. But I don't think the event plane bias is driving this here. I mean if I can go to the plot that's sort of used, this is the plot I use to motivate things here. There's a V2 plot and P-LED. Hopefully this is displaying for folks again. We really looked at this for a very long time, and you can see that there's 3 different selections here. So there's like high PT jet selections, but there's also minimum bias triggering. And while there is a difference in like the intermediary V2 observed with depending on whether you select on a trigger versus not, there's a lengthy discussion in the paper of why this is the case, why this trigger is these differences in the V2 distribution in intermediary PDs are pretty understandable actually, and that the high PT behavior is consistent all 3 as expected. I don't think event plane stuff biases related to the event plane can do this. That said, maybe it can, and that's why we're always sort of like poking and prodding at these analyses and making sure we understand everything. I don't think it's the case here, but would always welcome someone being able to demonstrate that they know better.
I'm not claiming that.
No, I know.
I have nothing to add. I'm just asking.
Yeah. Well, this definitely is, I think everybody agrees, this is a puzzle that still need to be really carefully examined. I have actually another comment here. Can you go back to like your slide 29? This is about, this is about the medium response. And we actually did calculation with, coupled hydro, there's a coupled LBT.
Yeah.
And then there we actually can describe your data, and hopefully maybe I don't know whether we have sent you data the calculation or not. The comment here is that the particular for hybrid model is very strange model. He does, if without a wake, he does not have, he just like have loose energy, so he only have a suppression of leading particles. And without this wake, he does not even have radiated glow inside the jet cone. So he put all the energy lost through elastic scattering or energy radiation into the energy deposition as a jet wake. So in a sense that when he calculate without wake, means he does not even have soft glows from the jet.
Yeah.
Yeah.
So
So the lesson, I mean, what we find out that even for this enhancement at low PT here, part of them is coming from the induced glow radiation, and a part of them is actually what we call truly, medium jet-induced medium response.
Yeah. So
yeah.
I think one of the reasons I really try to stress model dependence in being able to say anything about medium response is I think frequently these things are maybe the before and after implementation of these things is also hiding additional changes, like, as you say, the addition of more glue basically inside the emissions of the parton.
Yeah.
So it's a little hiding the ball to say, okay, this is the effect of the wake, because there's more happening frequently when they implement the wake. They add some other feature, and that's why it's difficult to make comments on this without considering the particular idiosyncrasies of the model answering the question.
We actually, have been, emphasized this a lot. Said that if you only look at it within the jet, it is very difficult to tell the difference between the induced radiation enhancement or induced the medium response. So what we actually proposed, in a recent couple of papers, is that especially when Z jet events, you look away from the jet, but looking at the Z side.
Yes. This is the CMS, and CMS has done this as well.
Yeah, and then and you try. It's very hard measurement, but I think if you can manage to do this careful sort of event matching, activity matching, you can do this background subtraction, and then you will see what we call the diffusion wake. Instead of enhancement, you will see a depletion of the hadrons in the jet direction.
I think you'll find going forward that we're gonna be looking at the near side as well. Yeah, because
and that is what we consider is a unique and unbiased way to look at the medium response.
Yeah.
Chris, I got to run. I'll see you Thursday.
See you Thursday, Peter. Very good talk.
Thanks for talking.
Okay. I'm also done with my question. Okay. I think we are way over the time, but
I'm sorry, I went long.
But no, that is okay. That's because we have so many discussions during the seminar. Well, thank you very much, Chris.
Thank you so much for having me.
Hopefully we can see some, you somewhere else in the workshop meeting somewhere.
Yeah.
Okay. Bye-bye.
Thank you for having me. Bye-bye.
Bye-bye.